is called accretion. So if you hear me use the words accretion, this is what I'm talking about. And when we detect these galaxies that have active black holes in the galactic nucleus, we call them active galactic or AGN. So if I kind of slip up and say AGN instead of feeding supermassive black holes, which is such a mouthful, now you know what I'm talking about. Another thing we'll be talking about in some of the stories we're covering are spectroscopies. I just want to give a little bit of a primer here. Every element, ion, molecule in the universe gives off light at a very specific wavelength or color. So if we could take a spectrum of the light, we can see those chemical fingerprints of that ionized atoms and molecules. So this gives us a way to learn about the chemical composition. Spectra also allow us to diagnose other types of conditions, including motions of gas. So if we see that this light from energized ions are shifted to where they should be in the lab, that can tell us about the motion. If it's shifted to bluer wavelengths, that means we're seeing stuff move towards us. If it's shifted to redder wavelengths, it means we're seeing stuff moving away from us. And sometimes when we take a spectrum, we see broader lines. Sometimes we see narrow lines. When we see broader lines, it means that the rotation of the gas that we're observing is faster, and that tends to widen the line. Keep that in mind, because that's going to come up in at least one of the stories that we'll talk about.
Okay. Are you satisfied that we have provided introductory material about black holes?
Yes, now I can get super nerdy and technical and in the weeds, and now y'all are going to be prepared for that.
Awesome. Okay, now, who wants to spin? Okay, the first hand I saw was your hand in the second row right there. And so you can be our first little spinner. We'll try to move around the room. Oh, I'm so excited. I can't wait to see what comes up. See all our names on me. Interesting. That's a double one. Which one is it? Beetlejuice, I'm so excited.
Right. That's not a black hole. How did that get on the wheel?
Oh, we'll see. Hopefully I will explain why. Since it's chaos order, I have to find the slides. Oh yeah, you can choose a piece of fun swag from our swag pile. Okay. This Beetlejuice binary star, that gives them too much away, so this is a better introduction. Okay.
Don't say the word again.
Okay, this is a story about everyone's favorite massive star that's going to blow up any day now, maybe. Betelgeuse. Okay. For those of you who don't know, Betelgeuse is a massive red star. It sits in the upper left shoulder of Orion. And the name Betelgeuse is sort of a weird quasi-mistranslation from Arabic, and it roughly means the armpit of the giant. But it's because, stars, most of the stars in the sky have these Arabic names, but they're not really the Arabic names. They're distortions of Arabic names that got translated into Latin, and often into Spanish, and then back into Latin, and then back into Arabic. They're a giant mess. So anyway, that's where Betelgeuse comes from. Betelgeuse is huge, right? It's incredibly large. It's maybe, so when stars are dying, especially massive stars, it's very hard to actually figure out what their masses are, but Betelgeuse's mass is probably around 18 times the mass of the sun, but it's a supergiant star, so it's more than 700 times the size of the sun for 18 times the mass. So for our little sun, if you lay an Earth side by side, right, it takes about 100 Earths side by side to equal the diameter of the sun. For Betelgeuse, you would need something like 70,000 Earths side by side across the diameter of the sun, and it's ridiculously luminous. Betelgeuse is around 500 light years away from us, so it's pretty far away, but it's still one of the 10 brightest stars in the sky, even though it's that far away, right? There's several million stars in that volume of space, and yet it's one of the 10 brightest. That's how bright Betelgeuse Betelgeuse is in the sky. And as Steph pointed out, Betelgeuse is not a black hole. And no, it's not, but it is a massive star. And when massive stars die, one of the products that can be left over from their death is a black hole. And the tipping point is somewhere a little more than half the mass of what Betelgeuse is. So Betelgeuse is very likely to be a black hole when it dies. So this will be a black hole story. But it's not yet a black hole story. So how long do we need to wait for this story about Betelgeuse to become a black hole story? Let's find out. You may recall a few years ago that everyone kind of freaked out because Betelgeuse dimmed dramatically, and it restored to its normal brightness over the course of about 3 years. And it took a little while to understand what was happening, but we now understand that it was a huge eruption of dust. And when astronomers say dust, what we mean is anything that's not gas or ice. Dust is stuff that's not hydrogen or helium. It's carbon-rich material. And this eruption of dust blocked some of the starlight from Betelgeuse, so it made it appear dimmer to us. The exact mechanism by which this happens is kind of poorly understood, because in general, the kind of death throes of massive stars are poorly understood phenomena. But it is, yes, this came, yeah, it erupted, and it's material. It's a reasonable fraction of a solar mass of material. Massive stars are when they die, they're like babies throwing a tantrum. They're really violent about it. And this is a thing massive stars do. Another thing that these kinds of stars, red supergiants, do is that they undergo pulsations that happen at regular intervals. So you get brightening and dimming in a periodic cyclical fashion. A lot of stars pulsate. And it usually means that they're approaching the ends of their lives when this happens, but it's part of the normal process of regulation of fusion in the cores of stars. If the rate of fusion decreases in the core because you're starting to run out of material, then the star will condense, which increases the pressure in the core, which increases the rate of fusion, and so the star will expand. This happens in a very cyclical fashion, and different kinds of stars do this all the time. Betelgeuse has 2 different cycles of pulsation. It has a cycle that lasts about 416 days, so a little more than a year, and it's a longer cycle that lasts 2,170 days, so that's about 6 years. This cycles of 2 different cycles of pulsations is not a thing that massive stars do. That's weird, and there's not been a good explanation for why that is happening. That was just this is Betelgeuse changing every time. But until now, in a paper just this past year in the Astrophysical Journal, this group of astronomers proposed that the 6-year cycle isn't due to this internal machination of fusion happening in the core of Betelgeuse. The 6-year cycle is because Betelgeuse has a companion star, a little tiny companion star, and that second star plows through the dust from the periodic eruptions from Jupiter. And that's kind of what's being depicted in the central panel of this little cartoon, which is actually in the paper. They released a press release image that was beautifully animated, and it's not as nice as this little cartoon that's in their actual paper, which I just love. They got away with putting this paper in the Astrophysical Journal. So we don't just see extra brightness or dimness depending on whether the companion star is on the front side of Betelgeuse or on the back side. We actually see more Betelgeuse's light from the path of the companion star that it's burrowed out through the dust as it's passed around through the star. So it clears out a path, and so you get a little extra brightening, and that's kind of what's trying to be depicted in the top figure of this. And they named the little companion star the Beetle Buddy. And they calculate that Beetle Buddy is just a bit more massive than the Sun. And it's orbiting at a distance around Betelgeuse of 1.3 billion kilometers. That sounds really far, and it is. But that's about how far Saturn is. And as we previously stated, Betelgeuse is real big. So this is practically skimming the surface of Betelgeuse as it's orbiting it. So here's a little graphic that kind of shows you Betelgeuse and where the orbits of the planets in our solar system are. You need to read it. It's my notes.
We'll wait on the light.
Oh, I'm sorry. On this, the outer circle of Saturn's orbit. And the one the interior that's Jupiter. Okay. Okay. Now we get to the selfish reason why I included this story in our panel. As I said, Betelgeuse will likely leave behind a black hole when it dies, and it has a companion star. So, no, this is supposed to be fine. It's fine. So Betelgeuse has a companion star. So when Betelgeuse dies, it will become what it was always meant to be, a black hole X-ray binary. These are the objects that I study for a living. These are little black holes that have companion stars around them, and the companion stars are donating material to the black hole, which through the accretion process Steph was discussing, forms a bright disk of material around the black hole. So this is fantastic, because this means these things are real far away from us. The nearest black hole X-ray binary that we have to us, that we know of right now, is 3,500 light years away. Betelgeuse is only 500 light years away. So this happens to Betelgeuse, we get one right next door. So I can't wait for Betelgeuse to die. Because then my evil plan will be complete. But, so back to this paper, right? 500 light years is not very far away. And so if Betelgeuse were not there, it would be very easy to see this little companion star, the Beetle Buddy. But because Betelgeuse is there, we have no hope of seeing a star that's the mass of the sun sitting right next to it. At least not very easily right now. Although maybe we will in future missions. But if this story is true, if this holds up, it has a really important implication. Prior to this, it was thought that shorter cycle. So it was thought that Betelgeuse was very late in its stage of evolution. That it was at a stage where it's fusing carbon in its core. And that means that Betelgeuse could die mysteriously any day now. But if the shorter cycle of pulsations is actually due to this little companion star around Betelgeuse, and the longer cycle of pulsations is the one that's actually due to the internal machinations of what's going on inside of Betelgeuse, then it's not fusing carbon in its core. It's still in the helium fusing stage in its core, which is much earlier in its lifetime. And so that means it could be 100,000 years or more before Betelgeuse actually dies. And it won't be any day now. Which means I don't get my X-ray binary after all. Unless I can learn how to cheat death. So that's the next part of the plan. Yes.
If that's the case, the assumptions about two cycles reverse, and the shorter cycles actually be movement of the tank star as opposed to the longer cycles, and they are closer to the orbit.
Yes, the shorter cycle, they think, is the one that's due. The shorter cycle is the one that's probably due to the planet. The longer cycle is the internal machinations. So that's why, yeah, it is super close.
So that's the same something. That's the same something. I'm sorry, I thought that you reversed the
Maybe I did accidentally. I don't think that I did.
Okay.
So yeah, the shorter cycle is probably due to this unseen companion, and the longer cycles.
That would put it at about a Saturn.
Yes.
So
Yeah, and the longer cycle, if the longer cycle were this unseen companion, it would actually be far enough away that we could probably see the companion. That would be very surprised if the companion were directly imaged because of how close it is to Betelgeuse. Yes?
So just to talk about Betelgeuse in general, isn't 500 light years a tad too close for our comfort for something like a creation of a black hole or a supernova?
So is 500 light years too close for the creation of a black hole? So from the black hole perspective, absolutely not. No.
No, I mean
Yeah.
for our health.
Yeah, no, yeah. For our health, we could have a black hole where we could have a Betelgeuse mass black hole where the next closest star to us is.
What the gravitational waves
And we wouldn't
radiation
care.
would-
The gravitational waves from creation, so gravitational waves are super weak and they dissipate relatively quickly. Gravitational waves are not a problem. The real problem from a nearby supernova is the particle flux from the explosion. The gamma ray flux maybe, but the particle flux is much worse, and particles travel slower than the speed of light, so none of us would have to worry about it. Whether it's bad for somebody in the future is not our problem. Okay, so that was our first story. Who would like to come spin the wheel next? You can place in the ring. You want to pick a person?
Over there.
If it lands on one of mine, just spin it here. It's gotta be one of your stories. That's mine. Spin it again. Spin better.
Alright.
That's you. Okay.
But you have to get a prize.
Yeah. Ooh, more prices appeared in the interim. This is exciting.
Oh, wait.
It's the very next story. Oh no, are you proving me wrong in real time? This is so embarrassing.
Checking. Space truck.
Wow, when did this happen? I totally missed this.
Yeah. I only knew about it because we did cover it on the past few times, so.
Oh, amazing. Whoever first pointed it out should come get a prize. You don't get a prize. I'm sorry, please talk about TDs. What's it?
I'm sorry to interrupt today, I came out.
Amazing. Oh, it's the right one. It's the short orbit. Yeah, that's fantastic. Oh, I'm so happy. I do. That's right. That now means I have to figure out how to live for 100,000 years. Awesome.
All right, next story. Let's define acronyms. All right, TDE is a tidal disruption event. So we see these events happen in galaxies that are hosting supermassive black holes, and when the star gets too close to that supermassive black hole, it can't withstand the gravitational pull of the black hole due to the tidal forces. That star gets shredded. That material then spirals off of the star onto the black hole. The center of the galaxy gets really bright, and this gives us a way to detect black holes in galaxies that were otherwise dormant, and we see that the light will fade gradually over time. So one of the defining characteristics of tidal disruption events are that they are from supermassive black holes, which we know are at the centers of galaxies, except when they're not. So that's what makes this discovery from the past year pretty interesting. This is a galaxy that's 600 million light years away. Right here is the center of the galaxy. Therein lies the supermassive black hole at the center of the galaxy. And in October or November of 2024, the Zwicky Transient Facility detected a flare from a point of light that is not at the galaxy center. About a month later, Chandra observed the same galaxy and saw this X-ray light coming from that point of light that's not from the galaxy center. Where this flare is coming from is from a tidal disruption event from another supermassive black hole that is in that galaxy. So if we look at this offset black hole compared to the one in the center of the galaxy, it is about 10 times less massive than the supermassive black hole at the center of the galaxy. So we've got this galaxy, two massive black holes. Why is one of them off center? Well, one possibility is that what we can be seeing is the remnants of two galaxy mergers, where each of these galaxies has a supermassive black hole in the center. They merge. The black holes have yet to merge. And so we're seeing this offset because that black hole still has to make its way down to the center of the newly merged galaxy. So this is an example of how TDEs, or tidal disruption events, can be very powerful probes to identify dual black holes in galaxies, especially because one of the questions we have are the roles that these mergers play in the growth and evolution of galaxies and the black holes that host them, that are hosted in these galaxies. Only two tidal disruption events outside the center of a galaxy have been detected before, and both of those have been detected based on their X-ray light. This is the first time we've detected a flare based on the optical light. But we definitely expect we are going to find more of these with the Rubin Observatory, which if you were in a panel a couple hours ago, we talked about what Rubin is going to do to detect these types of transient events. So this discovery gave us a way to detect a second supermassive black hole in a galaxy, which brings me to the next defining characteristic of TDEs, is that these result from tidal shredding of stars onto supermassive black holes, except when they're not. That's what makes this other TDE discovery from this past year pretty exciting. So in this video, we're going to zoom into the galaxy on the left. This galaxy is 450 million light years away, and we're zooming in on a star cluster on the outskirts of the galaxy. The star cluster is about 40,000 light years from the galaxy's center, and there was a dormant black hole in that cluster until a hapless star wandered too close by and get tidally shredded, causing a flare. So why do we think that this happened? It's due to the X-ray observations over the past 15 years of this galaxy. That purple light that you're seeing is the X-ray light from the star cluster, and that is coming from the star cluster, not from the galaxy center. And if you look at the brightness of that light, it is too bright to be from anything other than accretion. I use the word accretion because I defined it. Other than accretion onto a black hole, and it's so bright, it can't be from accretion onto what we call a stellar mass black hole, which is a black hole that is several times heavier than our own sun. It has to be from accretion onto an intermediate mass black hole, so something that is hundreds to thousands of times more massive than our own sun. And so what was observed in this star cluster is that there were a series of 3 X-ray observations over the span of 15 years. The first one was in 2009 at the Chandra Observatory. In 2012, there was another X-ray observation, and we saw that it got much brighter by a factor of 50. And then in 2023, it was observed again, and it got much dimmer. But it's just also kind of weird, right? Because I'm saying like, well, you know, TDEs are on dormant black holes. Why were we seeing X-ray light in 2009 before this thing got brighter? And there's a couple of explanations for that. One could be that this is something where maybe we caught in 2009 the very beginning stages as material started getting shredded, and then in 2012, several years later, is the brighter phase when the material circularizes and it gets much brighter, and then we're starting to see it dim again in 2023 as that material is getting eaten up. If we have additional observations, then we'll be able to see continual dimming, there's like a characteristic decrease in the brightness that we observe at teledisruption events, and that can help confirm this interpretation. So this is another example of how we could use these flares to detect black holes that we wouldn't otherwise know exist, and we can learn about their demographics. And again, with the Rubin Observatory, we're going to be detecting a lot more of these things to get to learn about the whole population of black holes, from supermassive black holes down to the intermediate mass black holes.
I love this result. And I love it because these intermediate mass black holes like this thing, HLX1, that's labeled, people try to explain these things as X-ray binaries, and that's not a great satisfying explanation, because why would this weird thousand solar mass thing, or many thousands of solar mass things that we don't know how to form, have a companion star? And this explains that away really nicely. I think this is a super cool result. This made me very happy when we included this.
All right, so the question was, if it takes time for this light to travel to Earth, how do we know that these events haven't happened long ago? And the answer is they have happened long ago. So we are seeing this as it happened however many hundreds of millions of years away I said that this galaxy was, right? So we are looking back in time. To us it looks new, but this is the snapshot in time that we're seeing that.
Betelgeuse could already be dead, yeah. It seems unlikely because of this little companion star, but it is possible, yeah, that it's already dead. Yeah, we should spin the wheel, for sure.
Spin.
Great, you have to see your hand very quickly, and then we'll come back over there.
All right.
That's you again.
Let's see. Oh, you got this. Right, he came up with that bumper. I'm not take credit for that.
I don't know what you're talking about.
All right, so a characteristic of some active galactic nuclei or free supermassive black holes is that they can launch these jets. They are powerful narrow beams of charged particles that are kept narrow or collimated by magnetic fields in the accretion disk of the black hole. They carry enormous amounts of energy, with particles traveling near the speed of light, and they impact their surroundings. Anything that they hit traveling at a very high speed is certainly going to be impacted. And we think that this is one way that these speeding black holes can shape the evolution of the galaxies that they live in, which is kind of remarkable when you think about it, right? Because these black holes, though they're supermassive, are teeny tiny compared to the galaxies that they live in, but when they're releasing this enormous amount of energy, that absolutely impacts its environment. So Centaurus A is a galaxy 12 million light years away and is launching one of these jets. And that's what you're seeing in this image, where the orange light is from the radio data and the blue light is from Chandra X-ray data. And that's where we see jets. It's the radio and it's in the X-ray. And one of the takeaways from this is that even though this black hole is teeny tiny, this jet is not only going through the galaxy, it's going beyond the galaxy. Tens of thousands of light years beyond the galaxy. So the Chandra X-ray Observatory has observed Centaurus A a whole bunch of times over the lifetime of its mission. And there's a research group that combed the entire archive of Chandra to analyze this data over 2 decades, from observations from 2000 to 2022. And part of that was to understand how this jet changed over time. So when they combined all this data, we got this, which is the deepest X-ray image yet of Centaurus A. And they found something new. To the bottom right, in this region, there's this V-shaped patch of X-ray light that's about 700 light years long. And what we think is happening is that as this jet is shooting out of the black hole, along the way, it's smashing into something. We don't know what that something is because we can't see it. Maybe it's some star that we're not able to detect, and maybe it's a gas cloud. But that collision is generating turbulence that ignites this X-ray light. And the shape that we're seeing might provide some clues about the object that the jet is crashing into. One of the things that I like about this story is because it really speaks to the power of what the Chandra Observatory can do. This is a discovery that can only be made with Chandra, partly because of its superb X-ray resolution that could really see these fine details, partly because of the long baseline of observations over 2 decades, and also because of its sensitivity. Chandra can observe this really faint X-ray light. By adding up all these images, it allows these faint features to pop out that you can't see in any one individual image. And I think this really illustrates the benefit of continuing to operate flagship observatories with unique capabilities that can do science that can't be done by any other telescope. Save Chandra.
That's a great. Yes.
Is there a reason why the plume on both sides of the black hole isn't symmetrical? So, I mean, the way that they talk about it is that there's a jet on one side and a counter jet on the other side. For the detailed reasons for that, I think we're still trying to figure that out, so I really can't give a ton of info about that.
Yeah, part of it is inclination, and so we see the jet that's coming towards us a little more than we see the counter jet move away from us, but that's not the full story in the case of Sene. It's a much longer story that definitely is outside of my area of expertise. We have friends who could probably tell you a lot about that, but yeah. Generally, when you see the asymmetric jets, it's partially an orientation effect and partially whatever stuff is in the intergalactic medium around the contacts that they're smacking into in different ways.
As any of these events observed from a different axis, we can usually take it, they're gonna have, let's say, we saw one from above.
So the question was, can we observe these things from a different axis? Like here you're seeing it kind of like this way. What if it's more oriented towards you? Yes, that is a class of the AGN called blazars, where the jets are oriented towards our line of sight. And that's a whole different type of AGN physics, which is a lot of fun for the people who